So am I audible?
Yes, ma'am.
And is my screen visible to all of you?
Yes.
Okay, good, very good. Okay, so in the last class, what we discussed? Do you remember? Do any of you remember what we discussed in the last class? Dave, are you going to say something?
Base and bound. Base and bound.
Ah, right. Good. So in the last class, we discussed, I mean, we have started our discussion over memory management, right? And we saw one important, I mean, if we want to virtualize memory, then basically we need to have some mapping of the virtual address space to the main memory, right? And how to manage it, what could be our memory management hardware, right? And we started with very simplistic assumption that each process has same size address space, right? And you are going to actually partition the whole physical RAM into that same size chunk, and then base and bound approach, using base and bound approach, you can actually maintain that. I mean, it's easy to maintain, right? So only just using two registers and one adder and one comparator, right? You can actually implement your memory management hardware, and that would help you to map virtual address to physical address, right? Okay, but that approach, since we actually we made very, I mean, simplistic assumption, of course, it's not that much realistic, right? In the last class itself, we discussed about some disadvantage. So this is the picture basically for base and bound approach, if you remember. So processor views that, okay, whole virtual memory is somewhere, right? It is stored in contiguous portion, but actually it might not be. But in, okay, but for at least for base and bound approach, we consider that whole portion of the virtual memory that is going to be wrapped in a physical memory that is in contiguous fashion, right? And the simple hardware was looks like this. I hope you have remembered this, right? Okay, but it has various disadvantages, right? One important disadvantage was internal fragmentation, if you remember. So what was the internal fragmentation? Does anyone remember what is internal fragmentation? So internal fragmentation, yes,
The
Akshay
memory
is.
memory is not freed continuously. So as a result, when memory is freed in blocks, it leads to fragmentation of free memory for the next process. So we might not be able to use that particular space.
Right. So the picture looks like something like this. So let's say this is the RAM, and I have allocated some part for, let's say this is for P0, and this is for another process P1, right? Inside this process, you will see you have basically many parts, right? For example, one part is dedicated for code, maybe one part is code, another part is data. Then we have stack and heap, right? And most importantly, the stack and heap part, that whatever we are actually we have allocated to some particular process, that might be unused, right? A large portion of that might be unused. So here I will have free space inside this process 0. A similar case will happen to some other process, for example, process 1. These are small memory which are free, but since they are inside some process, right? So you can't use it. So that's why it is called internal fragmentation. It is internal to a process, right? Process memory. You can't use it. Okay. But if you sum up all those free spaces, then it's actually come up to be a very may come up to be a very huge free space. And it might be the case that if you sum up those free spaces, it is actually it might accommodate one new process, right? So we should avoid internal fragmentation. That was one problem. Another interesting, I mean, some of the other drawbacks which we observe is basically we don't allow sharing codes or data among processes, right? So today we'll see how to do this, okay? How to, so basically we are going to see another method known as segmentation, okay? So there we'll see how to allow such kind of thing, Okay, and also we saw that accidentally it might happen that the process itself is actually overwriting its own code, right? So accidentally doing this. So that kind of thing we should prevent. There should be some mechanism to do that, right? And of course, another important interesting thing is since we actually assume that each process has fixed size virtual address space, let's say fixed size, it might be different for everybody, but you are since you are assuming this, no, so basically you are not allowing your all the process. So some of the process might need a huge amount of storage for its stack or heap, right? So that kind of restriction we had for the base and bound approach. So we'll see how to handle those approach. I mean, how to resolve these cons. Okay, how you can allow your stack and heap to grow as much as they want. Okay, so for that basically, so those are the disadvantages, right? Okay, so we have discussed this. Now, basically, now let's see how we can actually handle these issues one by one. For example, how you can allow your stack and heap to grow as long as they want, each process might want. Right? So basically, the approach, the segmentation approach, which we are going to discuss today, it's a generalization of base and bound approach only. So in base and bound approach, we have basically a pair of register, base and bound, right? Just a single pair of register. And in segmentation, basically what we are going to do here, since I am saying that this is a generalization of a base and bound approach, so here instead of looking the whole virtual space of a virtual address space of a process, a single entity, we can actually break down the whole address space into logical segments, right? So if you see this picture, as I mentioned, each process has actually 4 types of logical segments, right? Code is one part, then data is another logical segment, then stack is another, so heap is another. So in segmentation, what we are going to do, we actually we are referring a segment to be a contiguous part of virtual address space, right, which are basically logically same. So for example, code is a logical, so for a process, I'll be referring a code part of a process as one segment, data part to be another segment, stack to be another segment, heap to be another segment. So for each process, we would have 4 logical segments. Okay, so I hope you have understood this. Now, basically, since I said code, stack, heap, okay, here I didn't mention about the data part, so that you can include. So it will be just, instead of 3, you will have just 4, okay? Or maybe you can just consider code, stack, heap. You may consider data to be in heap somewhere, okay? But ideally speaking, data also should have, that is also another space, right? For example, if you declare array, right, you are not, so array of size, let's say 100, you can declare, right, at the beginning of your program. So that will come under the data part. So that type of segment also will be there. So now basically what we are going to do, so instead of maintaining just a single pair of base and bound, so since we have 4 types or maybe 3 types of logical segments, right? 4 types, let's assume that this is 4 types. So for each types, you are actually maintaining a pair of register, right? We need to maintain a pair of register, base and bound register actually. And now you can play with that, right? So for example, and the difference is basically, so if you're considering each segment to be each I mean code part to be a different segment, stack part to be another segment, right? Then the flexibility is you don't need to store the whole virtual address space of a process in a contiguous part of a memory, right? So you can actually allocate. You need to search for, I mean, where your, for example, let's say I have code part. It needs some amount of memory. If you find some free space of that amount of memory somewhere in your physical memory, you can actually locate that code part and load that into that memory, right? Same for the data, stack and heap. So stack and heap they are basically it's variable size. So depending upon the execution of your program, you might need your stack might increase, right? Or maybe the size might be decreased. Same for heap also, right? Okay. So very good. For example, let's see with some example. For example, if you see this picture, I think where is the picture? Right. So this is one picture. For example, here you can see for a particular process we have loaded the code part here, right? So in other words, so corresponding to code, that segment code for a particular process, the base register should actually store the starting address of code, right, which is 32K for here, and the size is basically 22K, right? Similarly, heap is stored over here. So, but here, so starting position is this. So you are going to store this, right? And same for stack. You need to store where is the starting point of stack, right? Okay, but here one important interesting thing is, so stack will, if you have ever implemented stack, you know stack actually grows in this direction, right? So maybe if you want to do that, then also you need to think about how you should manage it, right? So that we'll discuss. Just hold on for a second. We'll discuss how to handle that kind of thing. Okay. Now, I hope you have understood, right? So far, is there any trouble in understanding how this segmentation is going to work? So this is, as I said, this is just a generalization of base and bound approach. So corresponding to each process, we have a fixed number of segments, logical segments. So in this example, in the picture, we have just 3 segments: code, heap, and stack. But there could be another one also. You can just write data also in another part, or maybe here actually data is here they have merged the data and code into one segment, logical segment. But you can separate out also. Okay. Right. Okay. Now let us see the address translation mechanism for segmentation. It is also again going to be similar way. I mean, while we have implemented the base and bound, right? There is some difference, of course, because now the question is given any virtual address, right? So the virtual address will come from corresponding to a process, right? So now you need to decide first for which segment it is coming. Is it coming from the code part, or is it coming from data or stack or heap, right? So how would you decide that it is coming from which segment, right? So that's the main thing which if you are going to translate that virtual address into corresponding segment, means you need to map that, right? So that should be the first important point. Okay, any idea how to handle such segment, such thing? So the question is, so I will just give you one virtual address, right? Right. And now how would you decide that this virtual address actually it corresponds to code, or maybe it corresponds to a stack or heap? Let's say I have just 3, stack and heap, let's say. How do you decide? Just looking at a virtual address of a process. So if you remember the picture which we discussed in the last class, processor is actually generating this virtual address spaces, right, which we need to handle. So right, when we are going to execute some instruction, so either we are going to fetch some instruction to somewhere, or maybe you are going to load something in your RAM, or maybe you are going to copy something from your memory to some register, right? So then every time whatever the processor is generating, those are basically virtual address. Now, just looking at a virtual address, the question is how you can translate it into corresponding segment. Just looking at it. Okay, so any answer? How you can handle it? Hetty, yes, right. Extra bit you can mention, right? So that's one approach. Good. So what Hetty is saying, we are actually going to say that itself. So for example, I have, let's say, three types of segments, right, or maybe 4. So you can actually use for a virtual address. So given any virtual address, so maybe I will be using first 2 bit for and to determine whether it is coming from code or stack or heap. I will be using 2 extra bit, okay, corresponding to each virtual address, right? So first 2 bit will determine whether it is coming from code or stack or heap, right? So if it is, for example, if it is 0 0, then maybe it is coming from code. Otherwise 0 1, then it is stack. 1 0, then it is heap, and 1 1 means it's illegal, something like that. You can actually do that, right? I think I have written somewhere. Okay, right. So this is some kind of thing you can actually think about. Okay, now, as I mentioned, so last 2 bits are actually used to determine whether they are coming from which segment, right? Which of the 3 segments, for example. Okay, so once you have, now basically it's straightforward. You need to add the base, right? You can consider the remaining part as offset, right? Which you need to add, right? With what? With the base register, right? Corresponding segment. You see the base register value of corresponding segment. For example, if it is 0 1 stands for heap. So you see what is written in the base register corresponding to heap, right? You just add that value, this value, remaining value, and that will be your physical memory address. Right? Does it make sense to you? This is as simple as the thing, basically, right? Okay, very good. Okay, I have discussed this. Okay, very good. So basically, in other words, actually you can do this via this logic. How to go to a particular. So I will be virtual address is given, right? So you can actually use mask. So have you heard about this masking of bit? So if I have, so you can actually use mask, for example, 0 0 0, whatever you have, and if you apply AND operation, right, with this to this, then you will get this value. Okay. Similarly, if you just, so this is segmentation mask, let's say. So, right. I hope this kind of thing you have learned already. So this is one can do in hardware level also. So this I'll be using as masks for segmentation. Okay. Similarly, just opposite means if you want to obtain the offset, then basically what you can do, the mask would be 0 0, then all of the remaining things should be 1. So and if you just apply AND operation, right, then you will be able to obtain the offset. So given a virtual address space, you have 2 parts. One part is basically it signifies from which segment it is coming, and the other part is basically offset. So this offset corresponds to the with that logical address, right? Sorry, not logical segment. Whatever the base we have, we need to add this offset to go to the original physical location where it is loaded, right? Okay, so basically, given any, so first task, so you can actually construct your own hardware also, which will use this logic, which I have just mentioned. So it performs what? So given any virtual address, right? So it will basically first it will AND with the segmentation mask, right? And what is segmentation mask? Segmentation mask is, as I mentioned, this is 1 1 followed by all the zeros. Okay. So, and then you need to shift it. Shift it means you need to shift it towards right. Okay. Then you will get this. So that will be your segmentation number, right? Corresponding to that from where it is coming. Once you have that, then basically you go check the offset. So again, how will you obtain the offset? Offset, again, you can actually obtain the offset by performing the AND operation using the offset mask, right, with the virtual address. Then this will be your offset. Now you just check if the offset value is bigger than your bound of that corresponding segment, then you need to raise exception. I hope you have remembered the picture. Similar picture, right? You need to raise your exception if you compare the bound is going to be beyond your thing, right? It's illegal address, then you need to raise your exception. Same thing you need to do over here. Okay, same thing you are going to do over here. Otherwise, you just generate the physical address, right? And how to obtain that? That is basically you just go to the corresponding base value of that segment and just perform addition operation of the offset value, right? And that you can load into that. I mean, if you want to load something from that memory physical address, you just access it, load that into your register, right? So this is the thing. You can actually do this using your hardware, memory hardware. Okay, very good. This is one approach, so which Hetri suggested, right? So the approach is basically, the question was, given any virtual address, how would you go to the corresponding physical address, right? So this is one explicit approach, right? Explicitly you are maintaining some bits, right? Depends upon how many number of segments you have. For example, here we have 3 segments. We can actually manage this using 2 bits, right? That using 2 bits, right, extra 2 bits, you can perform, I mean, you can actually translate any virtual address to its corresponding segment, and you can actually go to the correct physical location. This is one approach. Another approach is implicit approach. So what is the implicit? What is the implicit approach? So again, the implicit approach is basically, so any idea what is the implicit approach? Implicit approach means basically, if you understand, so implicitly it will be decided, right? So now if you want, so since they are logical segments, so by actually how these logical addresses are generated, looking at that, one can decide whether it is for code or it is for stack or it is for heap. Okay. For example, if the address is generated from the program counter, right? So program counter will always actually stores the address location of instruction, right? So it means it will come from code part, right? So you need to go to the code segment only. So you don't need to perform this explicit approach. In that case, you can actually directly go to the code segment corresponding to the process, right? So this is interesting, right? Then basically you can avoid one stage. Similarly, if you understand the address is based off stack, right? Then you stack or base point or something like that. It is coming from a stack. Yeah, if you remember stack, corresponding to each process, you have stack, right? So that if it is coming from stack, then you know that it would be coming from stack only, right? Corresponding to stack. So you don't need to do this explicit operation. You can go directly to the stack, right? Okay, similarly, okay, if it is not coming from either of these type, let's say, then you can actually decide that, okay, maybe it is coming from heap. Okay. Okay, very good. So this is basically implicit approach. So ideally speaking, your machine might have both the approach. Means if you can understand that is those instructions or those virtual addresses which are generated from PC program counter, you should not actually apply to them this explicit approach. You can directly jump to the segment corresponding to code, right? Similarly, if some address is coming from the stack, then you don't need to actually apply that explicit approach. You just go to the stack, right? You can just minimize these operations, right? Okay. Otherwise, if you can't decide from where it is coming, then you need to apply it. Okay. Okay. Those, I mean, it's what should I say? It's a hybrid approach kind of thing. Okay. Okay. Good. Okay. Now, so the question which now I hope you have understood by this time how this segmentation is working, right? So how to, given any virtual address, how you are going to translate it, all the things is right. So now if you remember at the beginning, I told that the picture looks like this. You have a corresponding to process. So let's say this is given to the code and this is given to the stack, let's say stack, okay, and heap is given here. So heap will So if you give the starting address of heap, then basically that base address is enough for handling any virtual address which is coming from heap. You can actually add that virtual address. Sorry, you can just add offset, right? The offset which we, if you remember, the offset means this offset I am talking about. Now this is my offset for a virtual address, right? So this part is actually the offset. So if it is coming from heap, you know that you just need the base register of the heap, and you can actually add the offset value corresponding to that virtual address, and you can directly go to the physical address, right, corresponding to that virtual address. Okay, now for stack, it is, the picture is something like this. For stack grows just in opposite direction. Okay, okay, and so the base value of base register for stack would be this one. Say this is the stack. The memory requirement for stack is, let's say, this much memory is actually initially given for the stack corresponding to the process, right? So this address is basically now playing the role of base, not this one. Okay, the last entity, because it grows just opposite way, right? So if that is the case, then basically you need to perform instead of addition, you need to perform subtraction, right? Over here. So you perform addition. Okay, here I did not write. You need to perform addition over here. If I mentioned it earlier, I hope you have remembered that, right? So with offset, you need to, we were actually doing addition operation with offset and the base register value, right? Here you need to you need to do the just opposite, right? You know, if you want to get some address corresponding to stack, because stack is going just in opposite direction and the base is this one, so you need to perform just negation operation, not negation, subtraction operation, right? Okay, now the question is, how do you remember that corresponding to which segment you are going to perform addition operation, or which corresponding to which segment you are going to perform subtraction operation to obtain the correct physical address? So how to do this? Any idea? I hope the question makes sense to you and you have understood this. So what I said, so again, I have one virtual address, right? Then from that I need to actually obtain one physical address, right? Okay, now as I mentioned, all of the things are not growing in the same direction, right? For example, stack and heap are going in just opposite direction. So for example, for stack, to be specific, let's say it grows just opposite, right? So the base register value is the end of the stack, right? It's not the beginning of the stack. You are giving this end position, right? So in that case, you having any offset, right, which you obtain from virtual address, right, by performing AND operation, right, and with what, the mask, right, offset mask. You have offset mask. You just perform AND operation, then you will get offset value, right? In other words, that's the last, if you have the virtual address space. So if you just forget about the most significant 2 digits, the remaining things is basically offset, right? So you need to then subtract from the base register of the stack to this offset value, then you can actually reach the exact location, physical location. But okay, so some of them we are saying we are going to perform addition operation with base, and some of them we are actually saying that we need to perform negation operation, right? So how do you remember such thing? That's the question. Any idea what type of thing we should have in the hardware level so that you can do this quickly? Any idea what you should do, how to do this? Okay, so this one can do using just maintaining one extra bit, right? So basically you have, if you have, let's say, 3 types of logical segments, code, stack, and heap, right? So already you have base register value and bound somehow you are managing, right? And with addition to that, corresponding to each of these segments, so this is segment for code, this is for stack, and this is for heap, right? With addition to that, we can actually add another extra bit in that hardware, right? Just one bit. So where, let's say I'm putting, if it is 0, that 0 signifies we should perform this addition operation, okay? And 1 signifies we should perform subtraction operation, right? So in this way you can remember this, right? Does it make sense to you? Yes, right? So in the hardware level, you just have 1 extra bit. Very good. Just to remember, just to make sure that whether we should perform this addition operation or subtraction operation with the offset to get the exact physical address. Okay, very good. So far so good, right? We have handled most of the things, but now let's see another important question. At the beginning, we told that, okay, the base and bound approach did not support sharing. Now you want to make sure that this segmentation approach supports sharing, right? How would you make sure that this is going to happen? Again, the hint is something similar to this. How can you? So in other words, you in the hardware level, so how to support how to support sharing means, so would you allow everything to share with another process? And when would you do such thing? That's the question. Is it required to share all the things, all the content with other process?
I'm changing the permissions of all the segments.
Right. So we can actually add, right, good. We can, if you add some extra bit, so whether this is read write permission is there, let's say sharing permission, whether this is shared with something, right? If you are allowing this or not, right? Then using that actually you can maintain this sharing support, right? Code sharing you can, right? Protection bit, we are referring this as protection bit. So for example, code. So it should not be the case that code part of a process you should not give write permission to some other process, right? Or maybe that process itself. It should not write its own code, right? It should not destroy its own code. It should be in read execute accept, right? Permission, not accept, permission. So in other way, if you are maintaining this protection bit, it also solve your another problem, which we mentioned at the beginning, that in the base and bound approach, it might happen that accidentally some process is rewriting its own code, right? It might happen. So here you are not allowing that. You can actually manage that via using this protection bit, right? So this protection bit is very much important, right? This is in the hardware level you are doing this, remember. So is right, because operating system is a software only, but it's the basic software, right? So you can't do many things with it in the software level, right? So you need some hardware support for that. Okay. So good. So far, so good. Very good. So now basically the picture looks like this. If you understood the segmentation, so processor's view is this one, right? As if processor it is viewing that, okay, my code, data, heap, and stack, they are okay. They are in the consecutive memory. I don't bother where they are coming from, right? Where they are stored. But actually the picture looks like this. You have implemented this using this. So processor is producing some virtual address, right? Then you are performing this AND operation over here, right? You have offset mask for segmentation offset, as well as offset segmentation mask and offset mask. Both of these things are there. Offset mask, right? So you perform AND operation, right, to get the segment bit and offset bits, right? So this, once you get the segment bits, then basically you go cut to the corresponding segment, right? So that segment bit will actually allow you to go corresponding segment, and you see the base register value of that. You perform addition, right? And you can go directly to that location. And in between, before that, or maybe after creating this physical address, you can check with your bound register using comparator whether it is inside the bound, right? Otherwise, you can raise exception. Okay. Okay. So this is the picture. Basically, it is almost same with base and bound. Just as I mentioned, this is a generalization of base and bound. You have instead of one pair, you have multiple pairs, but it is constant number of pairs, right? Constant number of logical segments you have. Okay, now the question is, as I mentioned, if you are going to allow sharing, then the picture would look like this. So to be specific, we are going to allow sharing with another process code part, right? It might happen that code part of a process is shared by another process, right? So if that is the case, so you don't need to store two code segment for two different processes. For example, let's say I have one process whose virtual address is this, another process whose virtual address is this, and code part is basically shared. So you don't need to have two copies of the same code, right? You can have one single copy, right? And you are allowing that both of them will be able to access the code part, okay, by using of this protection bit, right? Since you have the protection bit, you know that anyway another process, even if they are going to access it, so they can't modify it, right? Does it make sense? Okay, to be specific, if you remember, so when we actually we talked about fork, right? I hope many of you have started experimenting with fork, right? Fork is very interesting system call. So when we just evoke this fork system call, if you remember, one child process is created whose all the things are identical with almost everything is identical with the parent process, right? So right, so all the things are identical except few things different. So for example, the value which is returned by fork, that is going to be different with parent and child, right? So for parent, that return value would be the PID of the child process, right? And for the parent, this would be just 0, right? If I remember it was just 0. Okay, so if you apply base and bound register approach, right? So in that straightforward approach, you might have to copy all the things twice, right? But since in this segmentation approach, you have learned that we have logical segments and all, what we can do, we can actually implement fork efficiently. You don't need to copy whole virtual address space, right? So maybe initially what you can, since all the things are same, so you can give all the things. I mean, you don't need to write it. Just you change the base and bound registers corresponding to the code, data, heap, and stack part of a process. I mean, that newly created child process, and let them initialize with its parent, right? That would be enough for us, right? So, and whenever you need that, okay, you see that, okay, you are actually going to change the code. Maybe it might happen the child's code is not the same as the parent's code, and you know how to do this, right? That also discussed. So if that type of thing is happening, and if it is needed to change, I mean, it might happen that the stack part or heap part also you are going to change, then only you should create a different segment, right? New segment corresponding to the child. Until and unless it is not required, you don't need to give extra memory space corresponding to that segment. Okay, so that's another efficient way to implement your fork. Okay, so this is known as copy on write. Means whenever you are writing, means you need to write something in your segment, right? Which is of course it's going to be different than your parent process, right? Then only you are going to write. You are going to copy it. Okay, and in other sense, you are going to create a new memory space corresponding to that segment. Okay, otherwise you don't need to do that. I hope it makes sense to you, right? So what we are going to do in other sense, copy segment table into child process, right? So in the proc structure, you have this information. So you just copy that only. You don't need to copy the whole memory, physical memory twice, right? Okay. And mark parent and child segments read-only. Of course, you need to mark all these bits, protection bit, all the things. Since you are now going to share with another process, right? You need to make all these read-only, right? Okay. The moment it is going to change it, then you realize, okay, so now you need to basically make a new copy for that. It is not allowed right now. Okay. So if child or parent writes to a segment, right, then trap is happening, means trap to the kernel is happening, and operating system will do all these things. Means you need to make a copy of that segment, and you can resume the process, right? Does it make sense? So this is one efficient way to implement your fork, right, using this segmentation. Okay. Okay, very good. Any questions so far? No question. Okay, very good. So we can proceed further. Okay, now the question is another important question. So if you understood this segmentation, right, the thing is we need to, we mentioned in the beginning that it is not required that all the stacks, I mean, stack can grow as long as it wants, right? Same for heap, right? So how to handle such things? So for example, let's say I have, we actually initially we allocated some part of your memory for your heap or stack, right? Later on you realize that you are actually out of bound, you need more space for stack or maybe for heap, right? Then how do you, how operating system should handle that thing, right? Does it make sense to you? So what would be your answer in that case? Do you have any answer? How to handle that thing? No answer. Okay, so then basically segmentation fault will occur, and it means, so if you understood, this is kind of then basically you need to change your mode, right? Mode of the processor, right? And it will be in the kernel mode, and operating system will do something on behalf of the process, right? Okay, I hope this term segmentation fault, you have already seen this before when you have implemented some programming in C or C++. Have you seen this segmentation fault before, this
Yes,
term, right? When did you see it?
When we try to sort of write on memory that we have not allocated.
Right. So basically, yes. So when segmentation fault will occur, right? Okay. So let us see. I mean, we will discuss this in detail. So when the segmentation fault occurs. So basically, if you understood, right, if you understood when, so the size of heap and stack is basically, it's not fixed, right? Initially, some part of memory is given, and that how much it depends upon how you are designing your system, and how the designer will decide. It will decide depending upon your workload, right, of your environment, right? So some part is given, let's say, right? Then you realize, okay, now you need to grow more, right? So what you should do, you should actually ask for more memory space, right? For that segment, means either for stack or heap, right? Then operating system, last day also we discussed that we need to maintain a list for free list, right? Free available memory, there should be some mechanism to manage that. So you'll ask for free memory, right? And if it is the case that, of course, you ask for more size memory, right? Compared to the present size given to your segment. For example, let's say it is heap, let's say. Okay, then this this free space management system, that is also part of operating system only. So they will look for some free space. So if it is successful, it will give you, right? And if it is not successful, then basically segmentation fault will occur. Means then you are saying that, okay, there is no free space which you can give to your process. Means segmentation fault is there and you need to stop the process. Okay, does it make sense? Okay, so now let's say you were able to find out some free space, right, where you actually accommodate your heap now, right? If it is the case, okay, so the picture looks like this, for example, let's say. So for example, let's say this is the heap part, right, occupied by your process. So you now, this is not sufficient for you. So you ask for a bigger size of heap, right? So let's say this part of memory was free. Okay, this part of memory was free and it is allocated to you. You ask for, maybe you are not asking for arbitrary size memory. So if you, let's say your heap was of size k, so you are asking for some constant time k, maybe 2k size memory you are asking for. Okay, and your system actually was successfully, I mean, it was able to find out some free space, contiguous free space of 2k size, right? Now it is to be allocated to your heap, right? So here you need to copy your existing heap, right? And you need to free this space, right? So, and since it might happen that some part of this is actually maybe leaked to some other process, because it is free, you are actually declaring this as free, you need to reset this to 0. Okay, means you just reset it to its initial state, whether it is 0 or maybe 1, all 1. Okay, let's say this is 0 or all 0 you need to do. That also you need to do. That is another step you need to do that. Okay. Then what the other thing you need to do? You need to modify your segment table, right? In the segment table earlier you had this as your base value corresponding to that segment. Now it should address this location, right? Not the earlier one. Segmentation table you need to change. Then you can resume the process. So all these things are taken care by operating system in the kernel mode when this segmentation fault occurs. Means initially I'm not referring to, so initially when the segmentation fault will occur, it will not give you the it will not give you this exception. Okay, user will not get to know about it. This segmentation fault or whatever you see, right? So that if you are not successful over here, right? If you are not successful finding this free space which your process is needing, right? Extra space. If it is not successful, then only at the end you are going to report it as segmentation fault. But this behavior, this phenomena, I am referring as segmentation fault. Okay, the term segmentation fault that is used in the programming, right? But that is basically if you are not successful. But this here the segmentation fault means here the segmentation fault means what? So you have a heap, right? Now heap wants to grow. Means the space is actually whatever the space it was given, it is actually exhausted. Now you need more space, right? Then segmentation fault will occur. So it means it's some kind of fault which we have already many types of fault, right? Last day also we discussed some kind of fault. So now you should have handler for each kind of fault. Operating system has some handler. Operating system will first handle this segmentation fault, right? It will ask for some memory from its free space management unit, right? It has some free space management unit. If it is failed, then only it will report segmentation fault, which you usually see in your program, right? You see sometimes segmentation fault occurs. Okay, that's the end. But here, basically, this segmentation fault into OS means similarly. If you remember, we had fault created by 0, right? Division faults, which we saw, right? Similar to this. Okay. Any fault, if some fault is occurring into your system, then operating system should have some code corresponding to that, right? Do you remember that? Trap table we have, right? So in the trap table, we should have a handler corresponding to this segmentation fault, right? And that will do basically this thing, memory management thing. It will ask for more memory corresponding to, the requested memory, whatever. If it is is successful, then it will do following things. It will zero your existing space. I mean, of course, it will not, first of all, it will not zero. It will first copy the whole thing to the new space, right? After doing that, it will change the base and bound register corresponding to that segment of that process, right? Then it will zero the memory, right? This should be the steps. So here I have not mentioned it stepwise, but I hope you have understood the stepwise manner how to do this, how this segmentation fault will be handled by operating system, right? Okay, good. Okay, now if you understood this segmentation thing, you have already seen these are the advantages, right? So the segmentation, it is allowing you to share codes in between processes, and how to do that, that also we explained, right? So if you are sharing, then it should be read permission, in read permission only, right? Once you need to change it, then basically you need to copy it, right? This is allowed over there. Again, I mean, this, yes, question?
Yes, ma'am. When you're mentioning that you can share code or data, so I have a question that in some cases we have to share calculations while the process, while the code is running. So when you say you can share code, are you also meaning that we can also share calculations meanwhile? Because in distributed.
Okay, so right, so yeah, so yes, so that's a good question. It depends upon the system where you are working, right? For example, you will see thread and all, they are basically sharing. It will mean not only the code but also the data, right? You'll see that when we learn thread, right? And it depending upon the system to system, it will vary, right? How you are going to allow the sharing. But the main point is you are actually allowing sharing over here. You can do that using this segmentation thing. Okay. And now it's up to the system developer how you allow, you are going to allow the sharing. So of course you can allow data sharing part, right? Code, data, stack also, as I mentioned for the child process, it is actually inheriting everything from the parent, right? So you should share all the things initially, right? Then the moment you are going to differ it from the other one, then only you are going to create the new segment for corresponding process, right? So in that sense, you can share everything, but you should maintain. I mean, you should implement this with care, so that, I mean, you by sharing, when you are allowing sharing, you should actually protect. There should be some kind of protection also should be there, right? So that in that kind of thing, right? Does it make sense, Akshay?
Yeah.
Does it? Okay. Yes. Good. Okay, so sharing is allowed, right? Then basically you are also stopping overwriting, right? And of course, transparently stack and heap can grow as long as they want, right? And you are allowing copy on write, which is better implementation for fork, efficient implementation of fork. Very good. But the question is, what is the disadvantage? Okay, is it, of course, is it the best whatever you can? Is there any problem in this system? That's the question. Okay, I have written it here, but I think you should not see it. Without seeing it, can you tell some disadvantage of this approach compared to the base and bound, let's say? What are the disadvantages? Any idea? Okay, for one important thing, actually, you need to remember, since these are all engineering things, okay, there is no that this is the best with respect to all aspects. Okay, it's hard to say something like this. There is always some kind of trade-off would be there. For example, here basically, if you remember, all the segments are of different size, right? Now, basically, if you are going to maintain the free space, right? Earlier, in the base and bound approach, so you actually imagine that all the processes are going to be of same size, virtual address space. So the maintaining of free space was very easy, right? All of them are same size, so you can handle it very easily. Now they are of different size. Now you need to maintain the free space. As I mentioned, there should be some free space management mechanism. So that is going to be very difficult, at least complex for this segmentation system, right? Where we are going to implement segmentation, their free space management is going to be difficult or complex job. I am not saying that it is not possible, but it would be complex. Okay. And another important thing is, since all of these are basically free space is basically now not free space, you have different size used memory, right? And you don't have control over where they are going to. Okay, can you hear me? So,
Yes, ma'am.
can you hear me?
Yes, ma'am.
So, but you can't see my screen, is it?
No, we can see it.
You can see it? Okay, because I am listening some voice. I thought that maybe my call dropped. Okay, very good. Okay, then I will continue over there. Otherwise, I was thinking that it is not. I think now you can hear my voice, but I think there is some internet issue over this small. I'll retry. So, is my voice audible to all of you?
Yes,
Yes.
ma'am. But screen is
But
not.
screen is not there. That I can understand. I'm trying to rejoin it. Let's see. Maybe I can change the internet. Okay, so yeah, since it is disturbing, so what I will do? So okay, what I can do? Maybe I can continue in my desktop. So in that case, I can't write it. Okay, am I audible? So, but my screen is not visible, right?
Yes.
So what I'll do, I'll try to share my content. I'll try to share my content from desktop. Okay. Share my screen. So is it visible?
Yes, ma'am.
Yes, right? Okay, okay, so good. But many things are there in my machine. So okay. Anyway, I hope this is visible to all of you. Okay, so as we were discussing, so in segmentation, the main problem is, okay, now the picture is not there. So you have basically external fragmentation. So what is that? So just opposite to internal fragmentation. So here basically in physical memory, you have you might have small free spaces available. Those are not part of some processes. They are basically free spaces. Okay, but but they're not consecutive. Okay, here and there they are actually scattered. Now it might happen that some process is requesting some contiguous part of memory for its some segment, right? And in your memory, again, if you sum up those free spaces, right, again it is bigger than the size of whatever the requested memory, but you will not be able to accommodate the request since you don't have that much of big chunk free contiguously. Okay, so this is known as external fragmentation. Does it make sense to you? Does it make sense? Please give some reply, because otherwise I can't see here. Basically, the problem is.
Ma'am, how is it different from the internal fragmentation?
Right, it's similar to internal. So the difference is in the internal fragmentation, if you remember. So those memory spaces were free inside a process. Okay, so now this is external because they are not part of some process. They are basically free to the operating system also, right? They are free in the free space management unit, right? But they are not contiguously free. Okay, does it make sense? So that's why the term is external. Okay, little holes of free space in physical memory. but it is difficult to accommodate new segments since you need more bigger chunks. So in internal segmentation, all the free spaces, whatever we talked about, so those were basically free, but those were free inside a process. You have allocated that part of memory, and though that part of memory is allocated to some process, but it is unutilized. Okay, so that's why we were referring that as internal fragmentation. And external fragmentation means it is not part of any process. You have not allocated that memory to anybody, so it is free. Okay, but so they are free. So in other way, you have so much free spaces. Those are actually neither used by any of the process. They are not given to any of the process, right? But you can't utilize them since they are not consecutive. They are not located in consecutive fashion. Okay, so they are. So this is known as external fragmentation. Does it make sense to you? Does it make sense? For example, there is a 24 KB free, but not in one contiguous location. Maybe I must have some picture. Okay. If not, I think you can imagine it. Okay, so now the question is how to handle such kind of thing in segmentation. If you have this external fragmentation, so any idea how do you manage this? Again, the idea is very simple, and I think you might have done this in hardware, in the hard disk level sometime. This is known as compaction. So have you seen this term before? I hope you have seen it. So we generally do compaction, right, in the hard disk, right? You might have seen that. Okay, in the memory utilization, you have so much memory here and there. Then if you just compact all those memories, they will be in contiguous location, right? So similarly here also, time to time, if you have this external fragmentation problem, to avoid this, the remedy is you need to do compaction. So what it will do? So if you need to do this compaction, then it will, of course, it should stop running all the process, right? Because you are going to move the memory, right, corresponding to each of the process, right, to somewhere else, so that all the used memories are contiguous, right? Does the picture make sense to you? Actually, I can't draw a picture. That's the problem. But I hope you can understand it. Okay, let's see this. Right, this is one example of compaction. For example, let's say this part is not used. This is the white parts are allocated, right? This part is not used. This is also not used. This is also not used. So there are actually so many free spaces here and there, right? They are not contiguous. So what you are doing? So during compaction, if you do compaction, apply compaction, then all these allocated memory will be in the contiguous portion, right? So you just compact this, right, and not utilized for free portion of memory will be also just contiguous, right? So in other words, you should map this to somewhere here, right, and you map this to somewhere here. Right? Since you are mapping all this, remapping all the things, you are reallocating the memory spaces, right? You are copying. So you need to copy some of the, right, swapping, all these things are involved. So this is a compaction is basically, it will take a lot of time, right? And while you are doing that, you need to stop all the processes. So, right, there is no other way to do that, because you are actually hampering all the processes at this space, right? Corresponding to all the segments, right? So in other words, the base register corresponding to each segment of each process, right, they might be changed, right? So that's why you need to stop it. Then you copy the data to somewhere, right? Of course, since you are copying from here to there, it should, since this is swapping, right? So it should have some swap space also, right? So if you want to, for example, this allocated memory to somewhere over there, it should be moved to somewhere first in the free spaces, right? Then maybe you can do it, or the otherwise, right? This is right. So in other words, this is a costly operation, this compaction. Okay, you are rearranging the existing segments in physical memory during the compaction, just to avoid that you don't have external fragmentation. Okay, does it make sense? Okay, so now the question is, yes, Akshay was asking something.
So in the left side, what you're showing is that non-compacted version. So
right.
In that, so whatever memory you are referring to is basically RAM, right?
Right. These are all physical memory, right? I am referring to this physical memory.
So
right.
when we have to do this compaction, we need a swap space. RAM is already full, so it means that swap space is basically.
So no. Okay. There is right. So that's the thing basically. So this compaction operation you should not do when the RAM is full, right? How? So it's not you're not going to do, because if RAM is all full, means you don't have this free spaces, then you don't need to do compaction, right? So you should have some small amount of spaces here and there, right? This is the one thing. Another thing, of course, you have raised one interesting question. So since I need to swap, I need to copy these to some other location, right? It should be the case I should take a backup of them, right? So what we should do, ideally I should back all this allocated part to a slower memory. Then you can take that and copy back to this memory, right? In that way you can handle this. So in other words, it is a really slow operation, right?
So basically it's an IO operation.
Yes, it would need some IO operation. Yeah, you need to go back. This is just, what should I say? This is a layman's term I am saying, but ideally speaking, it should not be that way also. So if you remember, have you ever installed operating system in your machine? There is a concept called swap space, right?
Yeah.
So in the operating system level also, we always keep some spaces for swapping purpose. Okay, so that space is basically used, and that space is basically, it's a fast memory. It's some part of your RAM only. We are going to use that. Okay. In layman's term, I said that you can actually do this via this, but ideally it should be, if you want to improve your performance, then this movement of this data, you should not do it to the lower level, right? There should be some space which you should keep it for this swapping purpose, and that swap memory is actually used for this purpose. Okay, does it make sense?
So basically, I was referring to that swap space only, because in most of the Unix-based OS, swap space is something that is on hard disk and
not on the RAM, right?
Yeah,
right.
It's basically on hard disk that has to be reserved.
Right. That one should reserve, and that should be some early spaces, right? It should not be here, right? So that is one kind of mechanism. Yeah.
If something is in the hard disk and we are copying it, so that's what I'm saying. Isn't it IO operation?
Right. It's an IO operation, of course. If you are going to, so again, it is a system to system. It will vary. So if you are going to manage via hard disk, so if you want to swap it back to the hard disk, then if you are going back to write this, of course, it needs IO operation, right? Without IO, you can't do this, right? You need to do IO. So that's why it's a costly operation. Compaction is costly. Ideally speaking, one should avoid that. Okay, in your system, you should not have this lazy thing, right? Because you are stopping all the process. There might be so many processes, so your system would be unnecessarily slow, right? Does it make sense?
Yes.
Okay, very good. Okay, any other questions you have? I hope you have understood segmentation. So I was thinking that we should proceed to, yes, question.
I also noted one thing. Let's say when we are working with big data, data that is big enough for the RAM.
Okay, and big enough for the RAM.
RAM, yeah, not that big. Let's say your RAM is 16 GB and your data is 20 GB, and you have a swap space of 16 GB again. So I've seen that what OS does is OS copies some of the data to RAM and some of it to swap space.
Space.
Okay. Yeah, it is not completely copying everything to swap space. Let's say 8 GB is on RAM now, and 8 GB on swap space again.
Okay.
How is this happening? Because what we studied is that you are saying everything is copied to swap space and then copied back to the RAM. Then how is it distributing data to RAM and swap space?
So if I understood the question correctly, so you are saying that you have so let's say I have 8 GB of RAM and 16 GB of data. Is it? Yeah. What kind of data are you talking about? Is it is it a part of code or something?
Yeah, it's part of code, because
right. So that's a good question. So far, so I have not discussed about right. So that's basically one fault of segmentation, right? So what we said, that's one good question which you raised. So if you remember in segmentation, what we are saying, we require one contiguous part of memory for your some logical segment, right? So now what would happen if your physical, I mean, if your code size is too much big, it is not fit, I mean, it is not good enough to fit in your physical RAM, right? So then basically this segmentation mechanism will not work, right? Because you are not allowing that, okay, some part of your code will be there, some part of code you may not actually take from your code, right? Ideally speaking, what you should have, some part which is actually used, right, frequently, right? Those part of code should be in your physical RAM. Not all the code should be in your RAM. So one answer to this question is basically paging. So in next class, we will learn, or maybe next class itself, we will learn paging. So that mechanism will allow you you don't need to, don't need to load all the, code at a time in your RAM, right? Rather the part, because if you see, you need to, at a time for a process, you are actually executing one instruction, right? Not more. If you have just one code, or maybe some constant number of instructions, right? If it is a multiprocessor environment, then why should you store all the part of your code or maybe big segment into your physical RAM, right? If you're going to do that, then basically you are not allowing a number of multi-programming, right? That you are actually restricting. So to answer this question, there is one beautiful answer to this. I mean, one approach to handle this is basically paging, which is generally implemented in now, I mean, in modern system. Okay, we'll discuss about paging in next class, next to next class maybe. Does it answer, Akshay? Do you understand this?
Yes, ma'am. But ma'am, sometimes there are cases when only the one particular part of the code, let's say we are on a particular instruction, that instruction does something that is too big to fit in a memory. Let's say there is around 7 to 10 million rows in an array. Okay. And there are 7 features for something. Okay. And you have to compute mean for each feature. Okay. Now, since mean is an aggregation function.
Okay.
So you have to know all the 7 million rows. Otherwise, you won't be able to do it.
Right. So I understood.
In that case, what happens is I observed in my OS, OS is distributing data, some of the data in RAM and some of them in OS, in swap. And I'm able to execute it no matter my RAM 16 GB and the data is 20 GB. I'm able to execute it.
Yeah, of course. So yeah, so that's another thing. So it's not only you are saying no. So we don't have only RAM and physical memory. In between also there are several types of memory. Actually, I did not draw the memory hierarchy that I should draw. So register is the fastest one memory, right? Which is in the CPU. Maybe after that you have this RAM. So in between RAM and this hard disk, you have basically cache. Okay, they are little bit, what should I say? It's little bit faster than hard disk. Okay, so what the memory management unit in general will do, it will not even keep all the things in your hard disk. Okay, so those, if it sees that these are the some of the data or code part which one should access frequently, it should move them to the faster memory. Okay, if you need to follow the faster memory, and the size is also like pyramid. So the fastest one has the smallest size, then the slower one, little slower, is bigger compared to the other one. It actually follow the pyramid style. I mean the size and fast, this parameter, if you just judge it, they will follow the pyramid. Okay. So, and of course the movement will also be in the pyramid style. Okay. And you don't, even if you don't accommodate all the things over RAM, then also it is fine, because anyway, if you don't find it, your system will actually go back via the path, and it will come back to that instruction or whatever data you have, and it will perform the operation. Okay. So once you understand the paging and all these things, then you will realize these things in better way. Okay. So hold on this curiosity. So I'm sure you will have this answer once you understand paging. Okay.
Okay.
Okay. Any other questions? If you have, do you have any other questions? Does anyone have? Because I think I have very little time, 15 minutes time. It's not. I mean, we don't have much time to start one new topic, right? I was thinking that we should also start discuss free space management, but I think it is. I mean, 15 minutes is not enough, so it's better to start in the next class. Okay. In that case, I think some of you wrote. Akshay, did you write to me regarding some question?
Yeah, ma'am. I sent you regarding the fork one.
Fourth one. Then that I can do. So did you find the answer? I gave you some hint also, right?
Ma'am, my OS it is running forever, so
It is running forever.
Yeah, it is printing out all the PIDs of all the child processes that are being generated, and it is running forever.
Did you try with small numbers? For example, I equals to 2 or 3?
Yeah, I tried with 10. I tried with 5, and then when I created the while loop, it creates so many processes that my system freezes, and then I have to restart. So it's not cleaning the processes on its own. It's just creating them. So that is
it is
what I
surprising.
was.
Maybe can you share me your code? I don't know. So in which language did you write? Can you write it in C and just check in your machine? So I think you are writing in Python. I can't check Python.
Okay,
So
ma'am,
just write your code in C and just send me the code. I'll check it, because it will not run forever, of course. And one can actually, if you understand how the fork is happening, how we are handling fork, right, then you can explain this phenomena also very nicely. Okay.
And one more thing. So let's say on some particular line we are forking that process. So the program counter will be at that particular line, right? And all the variables that have been set till now will be copied.
Right. Everything will be copied.
And then in the child process, whatever new variable that we are creating will die as soon as the child dies. So there is literally no way of saving this variable in some other variable in the parent process. So if let's say I have a variable A in parent, then I do the fork, then in child I set it to 10, then I kill the child.
Okay,
Now,
you are killing the child. Okay.
Yeah, now when I print A, it will be the value that was there in the parent, right? And not what I
Of course, no, yeah, it will print the value of parent, not the child process.
Okay, so the only way to make it consistent is that I have persistent is that I have to write it on disk, right?
You have to write on disk. Okay.
Let's say I have to save the variables in the child. I'm doing something.
No, you don't need to do something like that. So if you follow the code, whatever we have written, right? So I hope you have remembered the code. So fork,
Yes.
how to write fork, and then.
Yes.
So there is one mechanism to print the PID, process ID of the fork, and just print the process ID of the parent, right? So you will be able to perform this operation. And just run your code. You don't need to write something IO operation. You don't do that. Okay, how you have written that, I don't know. So there maybe you have done something. So
my question is something else. What I'm saying is that let's say I have to save some data in a variable. Okay, that variable already has some value in the parent.
That variable has already some value in the
parent. Let's say,
parent.
yeah, that variable is A and A has value 5 in the parent. Then I do the fork.
Okay.
After that. So now till now the variable value is 5. Okay, now I enter the child process. I change that value to 10.
Okay, you have changed the value to 10.
Now my question is there any way that I can remember this value without writing it to the disk? Because I already know I have to kill the child. That is the thing. As soon as
you have to kill the child. Okay, you can print it, of course, right? So before killing the child process, you just print it. The alternate way to write to the file is just print. Okay, just print the value of that variable and just print the PID. That's enough.
But for small cases, this will work. What if I have to work with the data? I can print it
that is also okay. You can write it into some file. Yeah, that's also perfect. But what is your question? I didn't understand. Yeah, that you can do. But
so for all the child processes, I'm creating that we don't use std out or print, and in the program itself we can save. Is there any way that we can save it
In
in
the
the program?
itself. So
Yeah.
program itself, where would you like to remember? Because if the process is dying, everything is dying, right? How would you remember this thing? So if you want to remember, as I mentioned, you can write to either you can write to screen, or maybe you can write to some IO file. I don't know any other mechanism to remember that. How do you remember? If the process is dying, everything is dying, right?
Yes,
either you need to pass this information to some other process, and if you want to know the user, how the user can know, the only way to know it, either you need to print it or you write it to IO. That's the only way. I don't know any other thing.
You said you can pass it to another process. How can you do that?
That I did not. I mean, I that you don't know right now, right? How to pass to some other process.
This is what I'm asking. What is the another way? You said you can pass it to another process. How can you pass this information?
There is some mechanism to communicate within processes. Okay, so that is out of the scope of present. The processes also can communicate with each other. There are some mechanisms. Okay, you can do it using pipes and other protocols are there. Okay, so if you really want to understand that, you can actually, you are encouraged to do that, explore that path. Okay, so process also can talk to each other. They can communicate. Yeah, okay. Any other question? Does it answer your question, Akshay? But you should write your code in C. Okay, and just write in C and check what is, I mean, if you just write it for I equals to 0 to maybe 5, how many times it is running. But apart from executing, I think if you understood the, I mean, how this fork is done, right? How the fork is implemented in the OS level, you will be able to answer it. I mean, you don't need to do the experiment at all in your machine. It's a thought experiment, right? Using thought experiment also, you can answer the question. I hope many of you actually already did this experiment. Akshay, is there any doubt, or am I audible?
Yes,
because I am seeing network quality is bad. Okay.
Yeah, okay. I'll see to that, because in Python, at least that I know, the OS is not cleaning the process. Even if you use even if you write OS wait, in parent, you are waiting.
I don't know Python. I told you at the beginning, maybe, right? So I will not be able to clarify your questions regarding Python. I'm so sorry. But if you have something regarding C and this fork, right? So please try your experiment on C and see what is happening there.
Okay?
Yes. If you still stuck over there, maybe you can raise your question and voice. I will explain it to you.
I had a doubt related to fork.
Hethi, your voice is not that much prominent.
I had a doubt related to fork. Can I ask?
Right. Go ahead.
Yeah. So I ran like the C code that was in the slides. I ran it on a bunch of online compiler, like online IDEs, and all of them gave the same output. And I'm not sure why that's happening.
Online, where are you writing in online platform?
So there are platforms like JDoodle and Replit, where one can also run compile and run.
Okay, so since these are online, you are running, no. So I don't know how they have implemented this online system. So it might happen. My answer to the question is, it might happen they saw this, the code is same. You have accessed or you have run the same code twice or thrice. Why should you run that again in the online server? Maybe they have the output stored over somewhere near to your location and sending the same data. That's my answer. But if you run that in your machine, you will see different answer.
Yeah, that is why I asked, because I ran it locally and then it was
different, right? So the answer to the online model, I mean, as I mentioned, so it depends upon how they have implemented the system. It might happen So they are smart enough to recognize that the code is same. So why I am going to run twice, thrice the same code there? So they are not running at all. They are running. They have the answer. They have stored somewhere. They are sending the same data. So that's why it is happening.
Oh, okay.
Okay, does it make sense?
Yeah.
Okay. Any other question you have? No question. Okay, if not, then let's conclude. Next day, we are going to discuss about free space management. Okay, I hope you have at least understood that free space management is also important, right? In the segmentation, you have so many different segments of different size. Now, free space management is complicated thing, right? So we'll see this in detail in the next class. If you have any other question, you may raise your voice. Otherwise, we are going to conclude it soon. Any other questions? No questions. Hetri, do you have more questions?
Not right now.
Okay, good. Okay, then if Akshay, Kartikeya, do you have any other question? Uddhars, right?
No, it's fine.
Okay, good. Thank you then. Yeah, Uddhars, do you have question? You raise your voice.
No, ma'am.
Okay, good. Okay. Okay, then good. We'll see in next class. Next class is scheduled on Friday, right? Friday at 5 p.m. We'll meet then. Okay, bye. See you. Take care.
Bye.
Thank you, ma'am. Bye.